video we are going to discuss about representation of discrete time LTI systems in terms of impulse responses. Okay, representation of LTI system in terms of impulse response was the first part of our LTI system topic, where it consists of discrete as well as continue. In this part we are going to discuss about the discrete time LTI systems in terms of impulse responses. Okay, in this video we are going to construct discrete time signal x of n. We are going to construct discrete time signal x of n in terms of discrete time shifted unit impulse. In this video we are going to construct a discrete time signal x of n. X of n is going to be constructed in terms of discrete time shifted unit impulses. We are going to split the x of n in terms of unit impulses. Okay, to analyze this we need a signal. Let us consider a discrete time signal x of n shown in figure below. Let us consider a discrete time signal x of n shown in figure below. Amplitude is 1 at n is equal to minus 2. Amplitude is minus 1 at n is equal to minus 1. Amplitude is 2 at n is equal to 0. Amplitude is 1 again at n is equal to 1. Amplitude is 2 at n is equal to 2. This is the given signal x of n. Now we are going to split this x of n in terms of discrete time shifted unit impulses. Okay, so let us see how we are going to construct a discrete time signal x of n in terms of discrete time shifted unit impulses, this x of n. Okay. Here we are having the signal. The signal x of n can be splitted as this x of n. I am going to split it as first one x1 of n. I am going to split this given signal as x1 of n, which is equal to x of minus 2. The first signal is at n is equal to minus 2, so I am going to take it as x of minus 2 into delta of n plus 2. X of minus 2 into delta of n plus 2, which can be represented as 1 at minus 2, minus 3, here it is minus 1, 0, 1, 2 and 3. This is x1 of n. The whole signal is splitted into a unit impulse, one impulse. As we all know, delta of n is nothing but the amplitude is 1 at n is equal to 0, and here we have got a delta of n plus 2. It means the signal has to be started at 0. N plus 2 means the signal is advanced by 2 units, which means the signal has to be started at 0, but it is starting 2 units advance at n is equal to minus 2. Advanced by 2 unit, 1 unit and 2 unit, advanced by 2 unit. So at n is equal to minus 2, amplitude is 1. Delta of n plus 2 is 1 at n is equal to minus 2. 1 into, here we have got x of minus 2 as 1. 1 into 1 is 1 itself. Okay. Remember, we have taken delta of n plus 2 just to represent the given signal x of n in terms of discrete time shifted unit impulses. So we have marked it in terms of unit impulse, unit response. Okay. Now we got x1 of n. Similarly, we are going to take the remaining values, x1 of n. The next one is x2 of n. Let us take x2 of n will be x of minus 1 into delta of n plus 1. As I said, firstly we took x of minus 2 into delta of n plus 2 for minus 2 value. Now we are taking it for the next signal. X of x2 of n is equal to x of minus 1 into delta of n plus 1. The signal will be minus 1 at n is equal to minus 1, and remaining parts are not mentioned. Okay. Similarly, x3 of n is equal to x of 0 into delta of n, or n plus 0, delta of n plus 0. Since x of 0 here we have got n plus 0 is delta of n only. After minus 1 we have got x of 0 only. Okay. That x of 0 value is 2. X of 0, the value was 2 into delta of n. As we all know, delta of n is 1 and n is equal to 0. Delta of n is equal to 1. 1 into x of 0, 2. 1 into 2 is 2 itself. Similarly, x4 of n is equal to, the next signal is at x of 1 into delta of n minus 1. Okay. We are having the value at 1. At 1 the amplitude is 1. So let us take at 1 the amplitude is 1. Okay. This is the signal. And delta of n minus 1 can be represented as for delta of n, amplitude is 1 at 0. Since it is delta of n minus 1, the signal is delayed by 1 unit. It has to be started at 0 and delayed for 1 unit and started at 1. The amplitude is 1. At 1, delta of n minus 1 is 1. 1 into 1 is 1 we got. Okay. Similarly, the last signal x5 of n is equal to x of 2 into delta of n minus 2. We'll be getting the signal at 2, amplitude is 2, that we got from the previous signal x of n. At 2 the amplitude is 2. Okay. So now we got 5 equations. X1 of n marked as equation A. After that x2 of n marked as equation B, equation C, equation D, and equation E. We got 5 equations. Okay. From these 5 equations, these equation A, B, C, D and E, we can write x of n as x of n is equal to x1 of n plus x2 of n plus x3 of n plus x4 of n plus x5 of n. The actual signal x of n was splitted into 5 equations: x1 of n, x2, x3, x4 and x5 of n, right? So now we are adding these equations to get x of n. Therefore x of n can be written as x1 of n is x of minus 2 into delta of n plus 2 plus x2 of n was x of minus 1 into delta of n plus 1 plus x3 of n is x of 0 into delta of n or delta of n plus 0 plus x of 1 into delta of n minus 1 plus x5 of n is x of 2 into delta of n minus 2, right? We have just substituted the values from equations. Okay. Now from this equation we can relate x of n. X of n can be written as summation of k is equal to, it starts from minus 2 and ends at 2. K is equal to minus 2 to plus 2 x of k. Okay. And delta of n, since it starts at minus 2 and here it is plus 2, delta of n minus k. Okay. Here we got minus 2 and here we got plus 2. We have taken k as positive, which means a plus 2 should be written in terms of minus. Okay. This we got the equation, marking the above equation as equation 1. This equation becomes equation number 2. Okay. In general, this equation is for the given signal x of n. Okay. If you want to generalize this equation, in general, x of n can be written as summation of k is equal to minus infinity to plus infinity, k is equal to minus infinity to plus infinity, x of k into delta of n minus k. Okay, mark it as equation number 3. This is the generalized equation that we are going to use in problem formulations. And this we have done it only for the input. Okay, but our LTI system, our time domain representation of our LTI system is to be representing the input in terms of output in terms of input. The main aim is to represent the output in terms of discrete time or impulse responses of the input. So let us relate the output to the input by the general equation. We all know x of n is fed to an operator h to get an output y of n for a discrete time signal. And this can be represented mathematically as y of n is equal to h of x of n. Mark it as equation number 4. From the above block, we can write y of n as h of x of n. Now substituting the value of x of n from equation number 3, Substituting equation 3 in equation 4, we will get y of n is equal to h of summation of k is equal to minus infinity to plus infinity x of k into delta of n minus k. Okay, but the operator h is operated for n, not for k, right? So we can rewrite it as y of n is equal to summation of k is equal to minus infinity to plus infinity x of k into h of delta of n minus k, marking it as equation number 5. Okay, from the above equation, since operator h for a discrete time signal, it is operating for discrete time signal n, so x of k doesn't contain any n terms, delta of n minus k contains the n terms, so operator h is operated for delta of n minus k. Now in the above equation, or in the equation 5, in equation 5 we have y of n is equal to summation of k is equal to minus infinity to plus infinity x of k into h of delta of n minus k, right? This is equation 5. Here h of delta of n minus k is the operation. H is an operator. Operator is operation performed on time shifted impulse delta of n minus k, right? H is an operator operating on a time shifted impulse delta of n minus k, which can be written as h of delta of n minus k can be written as h of n minus k. Operator h is operating on a impulse response, time shifted impulse, okay, which can be rewritten as h of n minus k. Now substituting the value of h of delta of n minus k in the above equation 5, we will be getting y of n is equal to summation of k is equal to minus infinity to plus infinity x of k into h of n minus k, right? Marking it as equation number 6. This equation 6 is known as convolution sum. This above equation is known as convolution sum. In general, this can be written as y of n is equal to x of n convolution h of n. That is equation number 7. This equation in general we can write it as y of n is equal to simplified form x of n convolution h of n, which means summation of k is equal to minus infinity to plus infinity x of k into h of n minus k. Okay, if you people have any doubts, please do message on my comment box. We'll be connected. Thank you.